Now, 3, 2, 1. Whee! Excellent. Well, not really.
Oh, it's in the
chip.
I'm in 4th place.
That's our game.
Yeah.
Fourth place with 0. You're wrong, but very fast. Okay.
Oh shoot, I got it wrong.
Why'd you add year, man?
Year.
I said.
Oh, you said.
I mean, that would be
Folks answer too fast. Inches per minute. Inches per minute is feed rate, not cutting speed.
Wait, I just increased place. How did that work?
Because you're fast.
Oh.
Nice work, but you dropped off the bottom.
Come on.
Oh, you guys lab me?
Okay.
Oh,
Here we go.
I just know it's got to be consistency of volume.
Excellent. Constancy of volume and friction. Good job. Most everybody there. Stress at and shear angle is not a terrible answer, but not the best answer. All right.
Oh, lab means gated.
Oh, because
Lexi having me.
Got it.
It is false. It's for the release of elastic stress, not plastic.
I'm still tired back.
No.
Okay. In one way, they're not super related, but they all have exactly the same resultant, which is the important thing. They are all ways of trying to look at the resultant and to understand it differently. All right, hanging on to a lead.
False. For sure.
Okay. Look at that. There we go. Nice work.
That's like tough.
Who won it? Lana. Nice work. Ayla.
Never been on the podium before.
Nope, not me.
Oh.
Certainly not me.
Back row winner. All right.
Like a told me a little learning goes a long way.
A little learning
Oh,
goes on.
your computer says you suck.
Yeah.
Your computer said you suck.
Yeah, it said a little learning goes a long way.
Oh, mine
It's
said
like all like last.
mine was asking like a tough game.
All right. So in a review, define cutting speed in your own words. Yes.
I said it was the speed of the workpiece relative to the speed of the tool. So like how quick
Okay.
it's moving past the tool.
Okay. So I like that, except for the word tool. I would like to get a little more specific there. Yeah.
The tool tip, is that what
Oh, wait.
I'd like a different word for tip, but we're getting closer.
The cutting edge?
The cutting edge, I like that, yes. So it is the rate at which the cutting edge and the workpiece material are moving past each other. Whichever one's moving depends on the process. And it can be that this is a rotary motion, but when you look at it on the microscopic level, you're just looking at how fast that cutting edge is moving through the material, so it becomes a linear motion when you zoom in far enough. All right, if a tool has a positive rake angle, which way is positive? It's leaning away from the direction of travel. Okay, so it's leaning back in this picture. It seems to me, I mean, I've shoveled a lot of snow, and it seems to me like the tool would get pulled deeper and deeper into the material. But that doesn't happen. Why is the tool not pulled deeper and deeper into the material?
The friction of the chip forming tries to push the tool out of the material.
Yeah, the friction of the chip forming is always going backwards and forcing the tool out. Now there is actually a set of circumstances that you can get to where it will pull the tool into the material, but is very rare. So you have to have such a low coefficient of friction between the material and the tool, and the rake angle has to be so far back that you have almost no normal force. So if it were a little tiny rake angle like this laid all the way back, there's almost no normal force, so then the friction is very, very small, and if you also have a low coefficient of friction, in this case it would dive. But this case is super rare because that tool is not going to survive very long. So it essentially doesn't happen. Okay? That is excellent. Graphics long after we needed them. But anyway, nice. Why is the shear plane important to machining? And how can we change it? Yes?
Like the plane across which like all the work is being done.
Okay, it's the plane across which the work is being done. It's where the material is giving up, right here. And it is shearing across that area. So how can we adjust it? Yes?
If the shear plane is shorter, then there's the amount of force that you put on that shear plane will be more, like, okay, wait. If you have the same amount of force, but the shear plane is shorter, then there's more force being applied to that one area on the shear plane. So you might like adjust parameters based on how long your shear plane is.
Okay.
So you don't end up with too much force on it.
Okay. Yes, but I don't like the word force there. The force is a little bit not quite right. Yeah.
Does it have something to do with like the amount of energy you're putting into cutting it?
Okay, so I'm putting force onto this, and energy is force times distance. And the force is kind of ish constant. Not really, but we'll say it is for a moment. And if I stand this shear angle up so it is shorter, then I have force times a shorter distance, that's less energy into the workpiece, so that's less heat. If I take the shear angle and I lay the shear angle way down, so it's starting at the tool tip and going way far through the surface, then I have a super long shear angle, or a super long shear plane, and so a huge amount of energy, a huge amount of internal heating. Now, I don't get to control that completely, because the harder material a material is, the more it's going to try to stand that shear plane up vertically. And so I am fighting against the hardness of the material. And so the way that I fight that, if it's making the shear plane too short, then I stand my rake angle up to neutral or even go negative. So when we're machining something like glass or a ceramic, very, very hard, very, very brittle, I can only machine those with a negative rake angle. So I lean the tool way over forward, and that's how I machine those materials. And in fact, what process do we normally use to shape glass? You know? Yeah.
Looks like diamond, like it's abrasive.
Okay, yeah, we use a grinding wheel and we use an abrasive. And if you look at a microscopic, so we have a giant grinding wheel here, and on the edge of that grinding wheel are all these little abrasives. And when I zoom in on this abrasive, that's such a sweet zoom tool. The bottom of the abrasive looks like this. So it's cutting with this edge and it goes ripping past. Well, that is mostly a highly negative rake angle. And that's why abrasive tools are really good at cutting those very hard, brittle materials, and why we use them. There are lots of other reasons too, but anyway, that is one of the reasons. Okay, so what do I do if I'm machining aluminum and the aluminum is welding itself to the end of the tool, which happens a lot?
You want to increase the rake angle because if you decrease it, it increases the heat on the
That's right.
part.
Yeah, so I'm going to take that tool and I'm going to lay it back. I'm going to increase that rake angle, take heat out of the process. So I would say that most aluminum tools, or most tools cutting aluminum, fail in what's called built-up edge, where we've welded material to the end of the chip. It's more likely to fail for built-up edge than it is to fail out of breaking the tool or getting dull. So depends on your machining parameters. But one of the things that you do is you're standing there not making very much money, so you think I'll make more money, so I'm gonna crank this thing up, let's go, giddy up, and then you start getting built up edges on the tools.
Is there a reason you would want to put more heat into the process, or is this
Yes.
just about managing?
Yeah, so if I'm cutting a hard material, I need to soften that chip to be able to not have it etch away the front end or wear away the front side of my tool. And so I will increase the heat in the chip to soften it. Yeah.
There's some animals there's not even a flute on it. It's just pure, you're just melting through the material.
Yes.
So that's just 100%.
Yes, we were cutting with a dowel pin the other day accidentally, and it works really well. It's surprising how well it works. You don't have to have teeth on the edge. Makes noise. it's not the best sound if you're expecting to cut anything. Yeah, but you can do it without any teeth at all. We don't do it very often. All right. Nice. Words. Okay. Merchant's force circle. Here is the point. The point of it is that there is a resultant force in a cutting process. The tool is either applying a force to the part, and the part is giving an equal and opposite force to the tool. So we have this resultant force in here. And we can break it up a lot of ways. That's the whole point of Merchant's force circle. So how might we break it up? Well, we can break it up into the cutting and thrust forces. The reason that we use these is because they're convenient for machining. I have the tool, it is moving through the material. I set up the direction that it's moving through the material. I force that to happen, and so it's easy for me to think in terms of those axes. Other than that, they're not a particularly meaningful set of vector pair to choose for this, because they have nothing to do with the mechanics of the process. They don't have anything to do with the material. It's just I can break it up into the cutting and thrust force, one pair of orthogonal vectors that sum to the resultant. Now, it seems like the one that is most useful or most meaningful, because this shear angle is where all the action is happening, and so it seems like the most useful pair would be the shear angle and the normal to shear. But the problem is, This changes all over the place. While I am cutting, there will be a little hard spot in the material, there will be a soft spot in the material, the heat comes, the heat goes. It's constantly changing because the dynamics of the machining operation are constantly changing. And until after the process, I have no idea what the shear angle was. We'll watch a video in a little bit where you can actually see the shear angle happening, but it is a terribly contrived thing to be able to see the shear angle occur. And so that one is the most meaningful from a physics kind of standpoint, but I can't actually tell what's going on during the process. Now, friction and normal to friction are actually pretty useful because I know the angle of the face of my tool, and so I can tell what the direction of friction is going to be, and then normal to friction is, you know, normal to it. So that is pretty useful, except that I would have to get those two, I would have to orient my force measuring system in kind of a funny way, because it would have to be tilted to match the rake angle of my tool. And there aren't many force measurement systems that want to be tilted that way. And so I end up with cutting and thrust as the things that I measure, and then I extract from those what the resultant was. I know what my rake angle was, and from that I can determine friction angles and normal to friction and get information out of it. Any questions about that? So they're not unrelated, they're all the same resultant. Yeah.
Yeah, so there's the shear force and
Yes.
the friction force, and those are not normal to each other?
They are not normal to each other.
Okay.
Yeah, it looks like they are in this drawing, which is a problem with the drawing, but when we watch it in a few minutes, you'll see that the shear angle changes all over the place, and we don't know that they're normal to each other.
Gotcha, so
Yeah.
we can't assume.
We cannot. That would be nice. Darn physics. Never doing what we need. All right, units of cutting speed. Surface feet per millennium, yes. No, surface feet per minute, all right? It is a funny set of units, very odd set of units. But the numbers are huge. We'll be talking about something with 1,000 surface feet per minute. And that's feet. And then all the other things are measured in inches or millimeters. So this one is a massive number in comparison with the others. And that's why I said the other day that there were these this weird intersection of things happening, and that is machining and nuclear explosions. And it is because the machining is happening so fast, it is deforming the material at this just mind-numbing rate compared to other ways that we do anything with materials. You can also get it if you firing artillery at something. And so that's actually how you do these tests, is a thing called a gas gun. And so you take a little chunk of material that's very, very, very hard, and you take the material that you want to test, and you put it in a big, long potato cannon, and it's like a scientific potato cannon, though, not the kind that you spray hairnet in the back and light off with a barbecue lighter. This is a lot more specific than that. But anyway, you launch it with compressed air. You generally would put vacuum in the line so that you're not slowing the projectile down at all. And it would go launching down and hit the part. You can see how fast it changes. All right, the feed rate is inches per minute. And that is the thing that we set in the machine. So we use the cutting speed to determine the spindle speed, and we set inches per minute. We just have to choose that. Generally, we will choose it off of manufacturer's data. We'll talk more about that next time. There's supposed to be some cool things coming up here. Oh, look at that. Sweet. All right, depth of cut. In freedom unit is inches. Chip velocity. Surface feet per minute, that's right, or feet per minute. Uncut chip thickness. Inches, right? Rake angle, degrees, nice. We'll skip the variables, that's okay. We can know the variables, but they're not so important for right now. Okay, so these are the things that we are setting and thinking about in our process. This question is about the lab today, so we can't say what we changed today because it hasn't happened yet. And we're talking about that later. Okay. That's important to know. Positive, negative, and neutral rates. That's like excellent work, right? I mean,
Did you draw this?
of course I did. Sweet graphics work right there.
It is.
I know. You can't just find this kind of stuff on the internet. You have to
My
make
bad.
this kind
I'm
of
sorry, I
stuff.
didn't recognize your artistry.
Yeah, I remember how I did that. Anyway, what is the difference between cutting speed and feed rate in an actual cutting process? Yeah.
Your feed rate moves with your spindle speed and everything like that, because it has to be within a set parameter of chip load.
Okay, so it is within a set parameter of chip load. We're determining how much we can, how thick a chip we can take without overwhelming our machine. But they seem really similar in a way. It's easy to get this confused. And the reason is because the directions sort of change on things. So I forgot my giant blue foam tool. That is terrible. But anyway, you should always have an end mill in every box that you carry around. Because that's a thing. All right, so I have this thing and it is turning. So I have this spindle is spinning. And remember, the cutting speed is how fast is this cutting edge going ripping past the edge of the material. So most of that velocity is because I'm turning it at a high RPM. I have a feed rate. So the feed rate is how fast is this tool moving through the material. And so the actual speed, the actual cutting speed is a superposition, is an addition of how fast is it turning with how fast is it feeding through the material. But remember, how fast it's feeding through the material is inches per minute, and it's on the low end of inches per minute, like 200 or 300 and below in normal machining terms. And the surface feet per minute is like in the 800 and above. These are sort of aluminum numbers. You can have a lot of different numbers depending on what the material is. But that's like 800 surface feet per minute. So if you were going for surface inches, you'd have to multiply it by 12. So we're at like 96,000 surface inches per minute. So the fact that it is moving, it is feeding through the material at 100 inches a minute doesn't matter in comparison with the cutting speed that we get from the rotation. So we neglect the feed portion when we're thinking about the cutting speed, and we just base it on how fast is this tool spinning. So in lab today and on Thursday, we are going to be spinning the tool at 10,000 RPM. All right. If you look on the charts, that's too fast. It's okay. They'll all be fine. Nobody will die. Oh. So we get to watch a cool video. We're actually going to watch it bigger. Let's watch it bigger. So, hey, stop. I said stop. Boy, you try to raise these computers well, and they just turn on you. All right, so just to understand what's happening here. Now I've confused it. All right, what is happening? We are acting like this is a lathe tool, and we have the material turning, and we are generating a chip right here as the tool comes, or the material comes across the chip, and it the material comes across the tool and creates a chip. Now that's not what actually is happening, because inside a scanning electron microscope, you can't make something spin very easily or very quickly. So what is actually happening is there is material, and it is being pushed through on a stage. Somebody's sitting there pushing the button on the stage, trying to feed it as fast as they possibly can, which if you've used the SEM is not very fast. And there's a tool mounted in there. Now the thing that's been weird about this is that they took this piece of material and they polished the edge of it. And you can tell that they polished the edge because you can see some individual grains in here, and you can see a collection of some interstitials around the edge of the grains, which is kind of cool, kind of interesting to see. And then they are running this tool through here, and it is kind of halfway sticking out of the part so that we can watch it. All right, so long explanation, lights off. Is that the right one? Yeah, that's fine. That's a lot of lights off. Okay, movie time. All right. Oops, sorry. Okay, so look along here. You can see the shear plane happening, and you can see that it varies some. It will be up here, and then it will go down here. Notice also what's happening at the tip of the tool. There's some material that's getting welded onto the tip of the tool. And if we look at the tip, well, no, can't do that yet. You'll look at the tip later. One of the problems with built up edge is that more it gets built up, it will sort of create a negative rake angle for machining the material. Let's pause this for a minute, just because it's cool. So pretty sweet, right? You can see the shear events that happen. The material built up stress, and then it sheared along the plane, and it sheared over. Look at the difference between the uncut chip thickness, which is sort of like this, and the cut chip thickness, which is huge, massive. Pretty cool, pretty neat. What else do we see? See anything else in there worth noting? So this is an uncoated tool. It's a high-speed steel tool, so should be fairly slippery. And you can actually make high-speed steel tools sharper than you can carbide tools, but we will use carbide mostly because they can go much faster. So it's all looking good, and then, oh, look at these things. So that difference in height right there is surface roughness that comes out because of having the rake angle not be correct. So that's causing material to build up on this edge. It's also somewhat because this cutting process is so slow compared to what a cutting process ought to be, that the chip dynamics are kind of wacky. Oh, that looks bad. It's going to be hard to recover from this one. We can look at the chips afterwards, and we'll look at chips in the next class. And you can look at this morphology, the shape of the chips, and you can tell things about the process. So this is becoming serrated chips almost, where the chips are separate. It's breaking into pieces that are separate from each other. We've now formed a completely new tool. We're not even using the tool anymore. So the tool wear has gone to 0 at the tip.
Is that all welded?
It is, but it'll break loose.
Or is it like, where it makes like where it like changes its height, is that buildup is all welded, or is it just getting stuck under there?
I mean, it's,
Or like the old
I would say it's hard to have a difference in definition. If it's stuck there, it's welded. So it's kind of a, yeah. So this one, the tool has a coating on it. Tin is titanium, something I tried. Iron. Look how it rubs the tool right here. So there's high temperature right here as well as high temperature at the tip of the tool. And then if you have a good process, it will actually cause the material to bend away from the tool further up. And what you want the chip to do is to wrap around and hit itself in the back. When it hits itself in the back, then it will break the chip loose. This is just, this is like a taffy experiment gone wrong.
Oh my god, it's so slow.
Yeah. It is, yeah.
I'm like making up attention. You know those photos of like water bears where it's like really up close?
Water bears.
That reminds me of it.
It's like mountain.
Yeah, this is bad. This is way too much heat. Look how low the shear angle is going way out from the edge. So we've got way too much heat in this process. And somewhat that's because the speed is all crazy on these.
It's like plastic.
It does look like plastic. We should call this plastic flow. Perfect. Good terminology. Unfortunately, no MERS were involved. No MERS.
What's
I
happening
know. The tools off to the left. It occasionally makes it into the picture.
Why are they showing this? This is embarrassing.
Look how bad our tools are.
Yeah.
When operated at this speed in a vacuum, yes, they're not very good.
Well, there's stuff in that one.
There are, yeah, there are inclusions, which is part of machining, is dealing with those inclusions. Cause they'll hit a tool and break off the end or all kinds of bad things. A fish?
I see it.
Oh, swimming?
Yeah.
Okay. I guess we can go with fish. Got a very pointy nose, this
Well,
fish.
what do you see?
I see a machine process. Sorry. Whoa. Yeah, so you're gonna feel that on the surface. That would not be pretty on the surface of the material. Right, here we go.
Ooh, can we watch Microscopic Splinter?
That one.
By popular demand, we'll probably.
I made this little widget, which is designed to cut metal, but it's designed to do that inside of a vacuum chamber of a scanning electron microscope, so that we can watch it happen in microscopic detail. And I have to tell you, this is some of the coolest footage I've seen in a long time. Right, so let's back up and talk about what's going on here. There are a lot of different ways to cut metal. Small milling machines, fancy 5-axis CNCs, or even a drill press and hacksaw. Fundamentally, the principle is very simple. You take something that is harder than the metal, add a sharp edge to it, and then push it through the metal. If everything goes well, you just cut some metal. Congrats! Now, of course, it's a little more complicated than that, but fundamentally, that's the idea. Cutting tools were traditionally made of a hard metal called high-speed steel. It's an alloy that is harder than older carbon steels and lets you cut faster, hence the name high speed. But high-speed steel isn't generally used anymore because we have a better material called carbide. This is actually a tungsten carbide powder mixed with cobalt binder. The powders are pressed together into a shape and then sintered. It makes a very hard tool that can keep a sharp edge. Cutting tools come in all varieties, although the common form is a cylinder with sharp fluted edges. The sharp flutes cut the metal, and the space behind the flute helps remove the material from the cut and eject it. There are tons of variations of this. You can have square edges or round edges, single flute or many flutes, super tiny or extra large, weird shapes, geometries that drill, and even though carbide is the most common, there are other materials too, like polycrystalline diamond or even single monocrystalline diamond. Sometimes the carbide is pressed into little shapes called inserts. That's what we're going to use today. These are 3 different cutting inserts, and you can see they all have slightly different shapes and coatings and materials. These little differences can have a big impact on how they actually cut the metal. To help demonstrate this, I'm going to cut some clay using an improvised cutting device. It's just a piece of brass that I've bent into a specific shape. And while all these folds look random, they all serve a specific purpose. The cutting edge is down here at the bottom. So if I take this tool and I push it through the clay, you can see that the clay starts to pile up at the base, and then once enough is accumulated, it starts to curl forward over top of itself. And that's what those creases and folds are for. As the material gets pushed up the face of the cutting tool, the little bumps and creases kind of push the material out and forward, which makes it start to curl back on itself. This is a useful property because it helps get the material out of the way. You want it to form tight little curls that are easy to break off and don't get kind of gummed up at the cutting edge. If you have a tool that has a flat cutting surface like this one, you can see that the material just sort of piles up on the face of the tool and doesn't really go anywhere. It kind of gets stuck. So those little bumps and creases are almost as important as the actual edge that's doing the cutting. So there's a lot of finesse into the geometry of these cutting tools. I've always wanted to see this in action under a microscope so that we could watch the carbide cut real metal and watch all these features interact with the metal in real time. And I wanted to see it under a scanning electron microscope because, I don't know, how cool would that be? So to do this, we need to make a little fixture to cut the metal inside of my microscope. This is what I came up with. It uses an off-the-shelf linear stage, which provides the cutting motion. That mounts onto a base, which also acts as a vise, holding our material to be cut. And on top of the device is the holder for the carbide cutter, which also allows precise positioning so we can adjust the depth of cut. Vacuum chambers are pretty picky about what goes into them. Most plastics and a lot of other materials will off-gas when you put them in a vacuum. So we need to clean all of our components really well by first degreasing it in an ultrasonic bath of simple green, followed by some solvent. The stage came with this green generic random grease, which I don't know what it is, but it's almost certainly not vacuum compatible. So we need to carefully make sure it's all been cleaned out and replace it with a vacuum safe grease. I'm using Molykote, which is a high vacuum grease. I mostly use it for greasing like O-ring seals, stuff that comes on and off of a chamber to make sure there's a good seal. But you can also use it for lubricate thing and moving back and forth. Reassembling this stage took far longer than I'm honestly willing to admit on camera. So we're just going to fast forward through all of that process and start talking about how this actually works. So first we mount the material that's to be cut. In this case, it's just a small piece of aluminum. Then we position the cutter with the help of a microscope. And finally, we advance the cutter 5 ticks on the micrometer. This moves the cutter forward about 50 microns. Because we're advancing this by hand with a little micrometer screw, we need to take a relatively shallow cut. In this case, I was aiming for between 100 and 200 micron, or about 0.2 millimeters. Then we pop it into the scanning electron microscope, pump down the vacuum chamber, position the image, focus, and finally take a photo. Then we pull it out and repeat the process, moving forward another 50 microns. I don't really know why, but I didn't think this would take too long. Like, I knew it would take a little while taking it in and out of the microscope, but I assumed it'd be like an hour or two and I'd be done. I was very wrong. This takes about 5 minutes from, putting it in the chamber to pulling it back out of the chamber and repositioning. And I took about 70 photos, so you can do the math. I was here for a little while. But honestly, I'm not even mad about it. It was totally worth it. I mean, how cool is this?
very smooth because it's burnished, it rubs against the tool. You can always tell on the chip which side cut and which side is solid.
So if you look closely and watch these stripes in the material, you can see how the aluminum gets stacked on top of itself. You'd think it'd be like peeling a vegetable, right? And the skin kind of comes off in one long continuous strip. But it's actually a lot more like that clay demonstration. As the cutter advances, layers get sort of piled on top of each other. The area where this is happening is called the primary shear zone, and it lays in sort of a diagonal to the cutting edge. There's also a secondary shear zone, which is all the metal that gets pushed up against the cutter's face. These areas are of particular importance to researchers because they have altered material properties compared to kind of the bulk metal. As the cutter is moving through the metal, it's displacing and shearing atoms in the lattice of the metal in those two different zones. And so you end up getting different arrangements of the metal after it's been cut. And the way that the shear zones interact with the cutter can be pretty important and change how the cutter performs. As the cut progresses, you can see that the backside where it's being cut gets cleaner and sharper. And then eventually the whole chip starts to curl over itself, which is basically those chip breakers in action. I have the cutting tool positioned basically perpendicular to the surface, which is known as a neutral rake angle. You can also have positive and negative angles, which will affect how it cuts the metal. If we go back to the clay, you can see that a positive angle has a pretty dramatic effect. It causes the clay to curl a whole bunch compared to before. And in contrast, a negative angle just sort of smooshes it into the clay itself and causes it to pile up at the base. There's no right or wrong angle. The rake angle that's chosen is often dependent on the material. Different types of materials and their properties, how hard or soft or gummy they are, will dictate what sort of rake angle you should be using. I really wanted to show the impact of the different angles and how it affects different materials, aluminum, stainless, carbon steel, but I couldn't do any more 7-hour imaging sessions. I just didn't have it in me. You can buy chambers for my microscope that have an electrical pass-through connection. So in theory, I could rig up some sort of like stepper motor to move the cutter forward and automate the whole process for me. But to be honest, those chambers are sort of unreasonably expensive for what they are. It's like several $1,000s for basically an empty box. And I just had a hard time justifying it for a project like this. If someone from Thermo is watching this and wants to send me one, you know, I'm all ears, shoot me a message, but otherwise I think what I might do is make some sort of like mechanical clockwork wind-up mechanism and use that to drive the cutter forward. So the idea would be you would wind it up ahead of time, put it inside the chamber, and then start imaging really quickly, and it just will cut as long as that clockwork spring is giving it energy. That would take a pretty significant amount of CAD work on my side, so I think I'm going to bump that to the future. It might surprise folks given the nature of my channel, but my background and training is actually in biology. Although I've spent the better part of my career working in software, specifically on distributed search and analytics algorithms. That's why you often see software adjacent projects on this channel, or some type of analysis of the data that's being collected. In the MEMS video, for example, I wrote a Python.
All right. Thanks, buddy. Enough of you.
More of his videos, please.
Yeah, so there are really, really good videos on breaking taps. Does a great job of them. So you should watch them. What am I trying to get?
Were you going to show us
here?
that anyway?
Sorry?
Were you going to show us that video anyway?
No.
Oh.
You folks just wanted it and it seemed like a good video. Move over. Oh, it's break time. Okay, so I don't know, like 53, 54, something like that.